Welcome to another video from algebra. We're going to be talking about the elementary properties of a ring theorem, or rings theorem. I took the liberty of writing the definition of a ring up here for anyone who needs a review, and we're going to go on with the theorem. So what's the claim? Well, let R be a ring and ABC be some elements of the underlying set of the ring. Then 1. It holds that A times its additive identity is equal to 0, is equal to the additive identity. 2. The additive inverse of A times B is equal to the additive inverse of A times B, and this is equal to A times the additive inverse of B, and this is equal to the additive inverse of A times the additive inverse of B, which is just AB. Pardon me, these are two different equalities, of course. They behave precisely as one would expect. And 3, if, moreover, R is an integral domain, that is to say that this means that if R commutes with respect to the multiplication and the additive identity is not equal to the multiplicative identity, or simply the identity element for each AB, which isn't equal to the additive identity, it holds that A times B is not 0. Right? It cannot happen that if I multiply 2 by 3 that I get a 0, not in an integral domain. Well, if R is an integral domain, then essentially the cancellation property holds. That is to say that A times C is equal, if A times C is equal to B times C, and C isn't 0, then is not the additive identity, then A is B. In other words, we can cancel out the C's. Right? How do we prove this? Well, the proof is quite easy, and one might expect with these elementary theorems. Now, so this really is more of an exercise. We have so we have A times the additive identity. Well, we can write this by definition as A times the additive identity plus the additive identity. This doesn't change the expression. And well, we know already that 0, the additive identity can be written out as the additive identity plus the additive identity. So here we obtain that this is actually equal to A 0 plus 0. We can ignore the other one, it will be useful later. And now, using the additive property of ring, which the distributive property of rings, number 3, we get that this is A times 0 plus A times 0. So we have that A times 0 plus 0 is A times 0 plus A times 0, or the additive identity if you prefer. Now, there exists an additive inverse always, so we can add it to both sides and get rid of this, and we arrive at the fact that A times the additive identity is equal to the additive identity. Okay, this was quite easy, so this was number 1. Number 2. Now, this is also quite easy. So, we have A times B plus the inverse element of A times B. Right. This is a fair expression, but what we can do, we can factor out the B, and now we get A plus negative, the inverse of A additive inverse of a. But this is then b times 0, and we have already established up here in number 1 that this is 0, and 0 can be written definitely as a times b plus the additive inverse of a times b by definition. So we get that a times b plus the negative of a times b is equal to a times b plus the additive inverse of a times b, right? We can cancel out these, and we arrive at the desired expression. The second one could be arrived at by analogy. Now, we will prove the third one, which will require a little more work, but not much. So, using these two facts, we have that the inverse of a times the inverse of b is equal to the inverse of a times the inverse of b is equal to the inverse of a times b, which is nothing more than a times b. Why? Well, the first equality is up here. Simply the minus signs are swapped because we started with something already inversing, and we know that the inverse of an inverse is the original, right? And then the second one is simply this equality from up here. And now we know that the inverse of an inverse is the original, which gives us the a times b. Okay, one last one. This one is quite easy. So take a times c is equal b times c, right? That's the equality up here from our claim. All right. From this, we get that the additive identity is equal to a times c minus or plus minus the b times c, right? We can take out the c, we can factor it out, we get c times a minus b. We know by the definition of integral domain that at least one of these must be 0, because two non-zero elements cannot multiply each other into zeroness, right? That's in the axioms of an integral domain. So we know at least one is 0. But we also assume that c isn't, right? So this means that a minus b must be 0. But then we get that a is equal to b, which is precisely what we wanted, and this concludes the proof.